Giant cones made of inflated Kevlar tubes, stacked together, may someday allow cargo, or even people, to land on other planets, or return to Earth. NASA calls this new spacecraft technology HIAD, Hypersonic Inflatable Aerodynamic Decelerators. But what's so special about HIAD? Find out more next on Real World. Engineers must conquer the challenges of designing an inflatable spacecraft and flexible heat shield that can survive the high speed and heat of entry into an atmosphere. High-tech flexible materials and inflatable structures are being developed in laboratories right now. But before they can be used to travel to Mars, we need to do some flight testing here on Earth. The Inflatable Reentry Vehicle Experiment, otherwise known as IRV-3, provided a flight demonstration of this inflatable concept. IRV is an inflatable reentry heat shield, which we're testing in the Earth's atmosphere. In 2009, we flew IRV-2, which was very successful, and demonstrated that we could inflate a packed vehicle to its full diameter in space, and that it would be stable throughout re-entry. Now we're testing IRV-3, which is the follow-on to the previous mission, and it will demonstrate higher heating using a larger rocket to launch a heavier payload, inflate still behind the same 3-meter diameter heat shield, but with significantly higher re-entry heating. That is relevant toward a re-entry on Mars. Whenever a spacecraft traverses an atmosphere to land on a planetary surface, whether it's here on Earth or at some other place, like Mars, the spacecraft must withstand tremendous forces and land safely to protect its precious cargo. An inflatable spacecraft could allow NASA to send more scientific instruments to distant worlds, since the inflatable expands after being packed inside a rocket. IT can deliver larger payloads. The inflatable spacecraft is draped with a flexible heat shield. The purpose of the heat shield is to slow down the spacecraft as it enters the atmosphere and protect the spacecraft from high temperatures experienced during re-entry. So why does size matter? Well, the larger the total diameter of the heat shield, the greater the drag force that's generated. You can think about drag as the resistance to motion an object has as it passes through the atmosphere. Several factors influence drag: the shape of the vehicle, the density of the atmosphere. But one factor stands out, mathematically speaking. Drag is directly related to the surface area. So when all other factors that affect the aerodynamics of a spacecraft remain the same, if you increase the diameter to double the surface area, you double the drag. This increased drag can then be used to slow down the spacecraft, allowing it to land where no spacecraft had landed before. Researchers and engineers apply math like this in the models and tests, but they can't rely solely on computer simulations. The computational models are good at modeling everything that we have a good understanding of. For a new technology, we really need to do a flight experiment to show that there are no unknowns out there that are going to bite us if we try to use them on a much larger payload. The HIAD team developed models, conducted simulations, and conducted tests in laboratories across the country, and then used these to predict how IRV-3 would perform. But on the ground, you can't simultaneously match all environmental conditions that a spacecraft will experience during an atmospheric flight. So the next step was to actually launch a HIAD on board a small rocket to demonstrate the technology with IRV-3, and the flight test was a great success. Engineers are now taking the data and knowledge they've gained from the IRV-3 flight and applying it as they look ahead to future HIAD applications. With each ground test and flight opportunity, those models are anchored and validated. It provides confidence. As we develop, the larger HIAD is able to transport more cargo. It's all part of the engineering design process. To get a payload that meets the mission requirements, we first need to come up with a design, analyze it, see how it will perform against the expected environment, and then we go a series of tests on subscale hardware to show each of these will work. Once the system has been shown to work, we put it all together and go ahead and do flight tests. The engineers have been transformed. The same basic technologies have been used for every NASA mission to Mars since Viking. But with HIAD, NASA engineers are really heating things up. With inflatable technologies, this could change the way we explore other worlds. See you next time on The Real World. And this credit goes to NASA, who shared this information. See you in the next video.